One. On Teams, can you guys hear me? Can you guys see my screen as well?
Yes.
Website, you see the website? Okay. So I want to start by talking about the test tomorrow. Make sure you understand exactly what to be expecting. So first is that it's going to be 6 questions, but the majority of your points are going to be within these 3 problems. You see an extended problem involving a derivative graph. You'll see one optimization problem, and then you're going to see a curve sketch problem. All right. And we'll go through one of each type today. Okay. There's 3 smaller, shorter questions that's they'll be related to 3.1, 3.4 quiz topics, so such as EVT, mean value theorem, or roles, or it could be a first derivative test problem, or it could be a second derivative test problem. Okay, open notes. You can. I'll encourage you guys to bring your calculator. Today we're going to go over some curve sketch problems. We'll go over some optimization problem, but specifically involving cost. These are the ones that are a little bit longer, so I want to make sure that you guys see that. So it'll be one of the optimization problems that we've seen up to this point, right? So I want you guys to be prepared for any of them. So definitely take some time to gather your information and your worksheets, as well as to be familiar with each of the types of problems. But today we're going to focus on the cost type. All right, so there's 2 things that I want to go. Actually, no questions about format of the test. Very okay. I want to talk 2 things specifically about tests taking for tomorrow, and this is geared mainly, addressed mainly to the virtual students, and it's the fact that, well, 4th period is a little bit longer than the other periods, so your test is going to be released when the bell rings, but then you have 10 minutes afterwards after bell rings to turn in your test. So, it's the same time as the other periods, but I would say that that you have to turn in your test within that time interval. So, if you're having trouble with Teams, then send it to me through email, or send it to me through Remind. Okay, or take photos of it, send it to me through Remind. But I'm not going to accept your test if it's after that deadline. Okay, students with face-to-face students have a time restriction, and that goes the same for virtual students as well. So I know, I mean, there may be some nightmare situations where you just suddenly everything just shuts down and your phone doesn't work and Wi-Fi doesn't work. So unfortunately, if that's the case, you're gonna we'll reschedule and have you take another version of the test another day. Okay, but this is also just I have to do this just to protect the fact that students in the classroom needs to be are held to a time limit, and so do students online. Okay. So any questions there? The second thing is that if you do experience a time crunch, I want to talk about what to focus on so that you know where the majority of the points are. So because not everything is going to be graded the same. So what I would say in general is I'm more concerned about the beginning and the middle parts of your problem. The end of each problem is not going to be worth as many points. Okay, so I would, if you run out of time, I would rather you run out of time at the end of each problem rather than, leaving a whole problem blank. So especially on the longer problems like derivative graph, optimization, and curve sketch problems, I'm going to talk about which parts I want you to focus on. And once you get to that point, move on, right? Because the rest of it is not going to be worth as many points. Get all your big points first, and if you have time, then you'll come back to those sections, right? But I'll tell you where as we go through each problem, I'll tell you at what point have you earned an A for that problem, and the rest is just smaller pieces. So if you're going to run out of time at the end of the problems. Don't run out of time because you can't. So I know it's tempting that you want to finish a problem because you've gotten up to that point, but I'll talk about where I want you to skip and then come back to it for later. So let's start off with the optimization problem involving cost. This is off the worksheet that is under today's link. So let me read the problem, and then we'll work through it together. It says a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of the base is twice its length. Material for the base costs $10 per square meter. Material for the sides is $6 per square meter. Find the cost of material for the cheapest container. So first thing we do is word, right? Keyword here is cheapest. It's describing cost. So we want to know what's going to be the minimal cost. Right? So we know that we're trying to get to the cost equation. Now cost is going to be associated with the material that we use to build the box, right? Or the container. And the box is going to be made up of surface area. So that's what we're going to be focused on surface area, and then we can merge the cost information into the surface area, right? Because it's the material that's going to cost money, right? It's not the volume that's costing money. It's the material that we're using to build the outside of the box or the container that's costing money. So let me draw a diagram first. So I have a base. The relationship is given to us that one side is twice the length of the other. So I'm going to call one side 2x and the other side x. The problem did not establish a relationship between the base lengths and the height, so we have to use a different variable there, so h. So it's the surface area that is going to be involving cost. So let's build the surface area first, and then we can work in the cost later. So surface area, right, we're going to be adding up the areas of each of the surfaces. There's only 5 surfaces, right, because there's nothing up top. There's no material that we need to spend money on for the top. So let's work on the area piece by piece. What's the area of that base? 2x squared, right? 2x times x, length times width. We have 4 vertical sides, but not all the vertical sides are the same shape or the same area. Let's deal with the side here. What's the area of this vertical side? X, yep, hx or xh, okay. What about the other side? Same, okay, so good. Right. What about the front-facing vertical side? 2xh. We also have a back-facing vertical side. That's also 2xh. So we're not memorizing anything, right? We're just building each of the sides as we come across it. Any questions so far? There is one more. There's another 2x squared up top. But why do we not include?
Oh, because
it's open top. Yeah. So if it's a closed top, that means we are actually going to spend money closing the container. But here we're not spending money closing the container, so we don't have to worry about any material for the top. Yes.
Just to clarify this, where did the 2 and the 2x come?
Right here. Oh, which one? This first one or this last two?
I guess on the diagram.
Okay, this right here. So it says that the length of the base is twice its length. So we don't have a square base. We have a rectangular base, and one side is twice that of the other. Good. Any other questions so far? Now, there's cost associated with each of the sides or the material that we've identified, or the dimensions that we've identified. So we know the base is going to be the more expensive one, right? This is the material that is going to cost $10 per square meters. So I'll put a 10 there. Now the vertical sides is a little cheaper. All this is $6 associated with it. So we're going to be multiplying these into the dimensions. And that's going to be that is going to help us build our cost equation. But I can combine these like terms, right? If I add these like terms, what does that give me? Yeah, 6xh. So we're going to focus on these numbers here. We have dollar amount associated with the side, sorry, with the base, and also we have an amount associated with the combination of vertical sides. So that is how we build our cost equation. So here's our cost equation. Put a star next to it because now this is what we're going to be finding the derivative of. Okay. Multiply the appropriate parts, 20x squared. 6 times 6 is 36. All right. Any questions here? Okay, so that's the hard part. If you can get to this part, then everything else is kind of feeling the same because then we're going to gather another equation, substitute the variable, and then the rest is all just kind of similar, right? But getting to this point is where the complexity is. Any questions? Okay. So we know we need some help, right? There's too many variables on the right side. We need to find a way to resolve that h. So we have some other information that's provided, and that is volume. So volume of a box is 10 cubic meters. Let's build our volume equation. Volume is length times width times height. Replace V with 10. Clean up our equation. Now we're going to solve for h. This reduces to be 5 over x squared. So here's my h equation. And this is what I'm going to use to substitute. Okay, so updating my cost equation here. My first goal has been accomplished. I've gotten my cost equation down to one variable with the help of my volume equation, but we're not ready for derivative yet, right? We want to go through our cleanup. We should be able to get this all the way cleaned up so that the only thing we need to use is power rule. Okay, go ahead and multiply that through. 36 times 5 is 180. But this we can clean up, right? So I can take out one of the x's. This becomes 180 over x. Continue cleaning up. I can make this 180 x to the negative 1 because I want everything to be nicely set up for my power rule. Okay, any questions up to this point? Okay, we should have an easier time with derivative here. Power rule, bring down the exponent, multiply by the coefficients, subtract 1 from the exponent. Bring down the negative 1 times 180. Subtract 1 from the exponent. And then we always set our derivative equal to what? 0. Okay, so this is where I'm going to ask you to stop on the test, move on to something else, and then come back to this if you have time. Okay. At this point, you've already earned an A on this problem. Okay, the rest is just solving for x, plugging in, and finding missing. But up to this point, you've shown me you understand the setup, you understand the calculus, you understand, right? Okay. So I know that maybe time crunch is not going to be as much of an issue in this class since you have a little bit more time in this class than others. But I would suggest that, you stop here and then move on to the next problem. But for now, we're going to finish this. Okay, so solving for x. Cross multiply. Divide both sides by 40. Reduce this to be 9 over 2. Take the cube root of both sides. So we have our x. Let's read the problem. What other information are they asking for? They're asking not for the dimension, they're only asking for the cost. So I have all these cost equations. Which one do I use? Does it matter? So any of these equations are fine. Okay. You just pick one of the cost equations and you plug in. They're all going to give you the same value. What you don't want to do is you don't want to be plugged into C prime. Okay, C prime is going to give you 0, and that's not what we want. We want to plug into one of the cost equations. Okay, any questions there?
So is the x isn't the answer, like it's just the.
X is one of the dimensions. It's this dimension here, but it's what we need to plug into one of the cost equations, right? But if you want to plug into the original cost equation, you have to find h first. So it's up to you. You can either find height first and then plug in, or you can use one of the adapted cost equations. Yeah, whichever one you want to use. Okay, any questions there? Any other questions? Okay, let's look at number 2. This is also optimization problem involving cost, but this is 2 dimensions. So if it's 2-dimensional, then we're not doing volume and surface area. Now we're doing area and perimeter. And your cost equation is now going to be built into the perimeter equation. Okay, so a manager of department store wants to build a 600 square foot rectangular enclosure, stores parking lot space in order to display material. 3 sides of the enclosure will be built of redwood fencing at $14 per foot. 4th side is built of cement block at a cost of $28 per foot. What dimensions will minimize the total cost? So we're trying to minimize cost. And then the building material, that is going to be perimeter related. Right, we're looking at each of the sides that's what's going to cost money, right? Not the area, it's going to be the perimeter. So I'm going to start assigning some variables here. Horizontal, I'm going to call them X. Vertical, I'll call Y. There's one side that's more expensive than the other. You can have it being the Y side. I'm just going to have mine being the X. Our middle steps numbers may look a little different, but in the end, it'll all be the same. So it doesn't matter if you choose the X or the Y. But I'm going to call this is going to be the more expensive material, and the other 3 sides are going to be a little cheaper. So cost is going to be similar to how we think of in terms of perimeter, right? We're going to add up all the sides, but we're going to include the associated cost with each of the sides. So 28x plus 14y plus 14x plus 14y. Combine like terms. Okay, questions so far? We look at our cost equation, we need some help, right? That y is sticking out, or we have too many variables either way. So I need some help. The help is going to come from this information here, 600 square foot. 600 square foot is related to area, right? This is a 2-dimensional unit. We know area is 600 square foot, so let's build our area equation. Area is just length times width, so just x times y. Make sure that you don't include the cost in the area, right? We don't want to say this is 28x times 14y. Right? We already have the cost involved with the material. The area is not what's going to cost money, right? It's the perimeter around that region that's going to cost money. Okay, so 600 square foot, that's going to be my area. I'm going to be working to try to get that y to be replaced. So this is what I'm going to be using to make my substitution. Okay, let's update our cost equation. Okay, our first goal has been accomplished. We've gotten this down to one variable, but now we want to clean up, right? We shouldn't have to deal with any messier rules than power rule. So multiply that out, I get 16,800. A little bit more cleanup on this fraction there. Okay, find the derivative. All right, bring the -1 down, subtract 1 from the exponent. I'm sorry, -2. Okay, derivative equal to 0. And this is where you can stop. Move on to the next problem and come back to it if you have time. Right? You've shown me that you understand all the steps. The rest is just kind of final things of cleaning up, solving for x, and then getting to what the problem is asking for. Okay. Yes.
Why do we cross multiply there? It looks like 0 is equal to 42 minus that. And then how does it change if we cross multiply?
Right. I just want to separate these two terms. So I'm adding the 16,800 over to this side.
I see it now.
Yeah. Okay, divide both sides by 42. Okay, I have my x. Let's go back. What information are they looking for besides x? They're asking for dimensions, so we want to have y as well. So dimensions, we need to see if there's a y equation. There is, so use that. We have our dimensions, 20 feet by 30 feet. And what other information are they asking for? Minimum cost. So minimum cost, we have to find one of the cost equations and use it. So either one of the original ones or one of the adapted ones. Any of these are good. Any of these will give you the cost that you need. Just don't use C prime. That's the one thing you don't want to use. Okay, questions there?
Can you scroll back up to the
Yeah.
first one?
I think I used this equation to build my cost. Oh, that should be squared. Oops, sorry, that's squared. That's right. This is right. This is right. Okay, anything else? Any other questions? Okay, let's go over to the other handout. So this is, you'll see one optimization problem, and then you'll see a curve sketching problem where I'm going to give you a polynomial, and I'm going to ask you a bunch of information, just like on the quiz, right? Relative max, relative min, using the first derivative test, finding POI. So I want to use this function, but what I'm asking for is not matching up here. So let's do this. Let's take this function and let's copy it to number 2, because I'll give you a polynomial. So why don't we do a polynomial for the steps involved with number 2? So let's cross this one out, and we'll just transfer this function over. Okay, find intervals of increase, relative max, relative min, concave down. So all that is with lining up with what we're going to be asked to do. So let's start off with f prime. Set the derivative equal to 0 to find your critical points. Take out a GCF. And factor this. Okay, set each of the parts equal to 0. Those are my critical points. Now we can choose some test points. Test against the factored form of the derivative. All we want is whether it's positive or negative slope. So -3, I get negative, 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 3 negatives, negative, negative, positive. So 2 negatives gives me a positive, positive, negative, positive. So only 1 negative. And then positive, positive, positive. Okay, so relative min at -2, relative max at 0, relative min at 7/4. Okay, we'll come back to this. Let's do second derivative sine line. Go through power rule again. Set equal to 0. Factor 6 out. Only 2 critical points. Create the second derivative sine line. Test values in each interval. Choose test values in each interval into the factored form. Positive would mean concave up, negative would mean concave down. Negative times negative, which is positive. Positive times negative, which is negative. Positive times positive. Notice that at this stage, when you set second derivative equal to 0 and you find your critical points, these are not yet confirmed points of inflection, right? In order to confirm a point of inflection, we got to force it make it go through a sine line, right? If there's no change in, we got to confirm a change in sign before we can call these points of inflection. But here we have 2 points of inflection. And now let's just go ahead and see if we can find all these order pairs and we can sketch the graph. So I'm going to find f of -2, I'll find f of 0, and I'll find f of 7/4. I'll find f of -7/6, and f of 1. So I'm going to dump them all into the original function. and see what y values they give me, and then that will help me have some anchor points to work with. So we may have to shrink our graph a little bit here. These are pretty large numbers. Okay, so -2 is all the way down to -44. So that's the lowest point, so I'll put it here. It's going to rise to a relative max at 0 and fall to another relative min at 7/4, which is close to 2, right? A little bit under 2. Somewhere here. Okay, you don't have to do anything to scale, just so we have an idea how the graph's going to look, right? We have our 2 relative mins and 1 relative max. From here, it should be enough for us to, oh, and that we can also plot these points too. -7/6 is -24.6. That's a little past -1. And then 1 is at -17. All right, so it's going to make my graph kind of go through those points. I'm not going to worry about my curvature just yet. Just want to connect them. Okay, but we have confirmed 2 relative mins and a max. Points and inflections, I'm going to highlight in red because this is going to be my transition points from one concavity to the next. So concave up, switches to concave down, and then back to concave up. I exaggerated my concavity there, but you guys get the idea. Any questions so far? On the test, it's going to ask for information about relative max, relative min, and it's going to ask you to write out statements. But I'm going to ask that you do this at the very end. Right? If you leave this, if you don't have time for this, it's minimal points. Right? So don't spend time writing it out until you have time at the end. Right? If you can get to the sign lines, the work, the graph, you've earned an A on this problem already. Okay, move on to the next problem. Save the justification and writing out all your intervals and all that. Save that for the very end. Right? You've already demonstrated you know how to do that on the quiz, so those will be worth less on the test. Okay, all right, let's do one more. And this is number 3. This is a derivative graph. you'll see an F prime or G prime. So we're just kind of hitting the big three of your tests, right? Now, if we're looking at a derivative graph, we have to understand that these points are not representing the location of the graph. So this isn't the shape of our original graph. We have to understand that this is representing the slope values of the original graph. So to help us understand what we're looking at, I like to label. Above is where positive slope exists for my original graph. Below is negative slope. Anything on the x-axis is slope 0. So I'm going to start off by building my derivative sine line. Sorry, G prime. My endpoints extend from -3 to 4. My critical points are going to come from my x-intercept. So that looks like a -2.5 to me. 0 and 2. Okay. Don't look at the shape. Don't look at the slope. Look at the location. The location from -3 to -2.5, all this is sitting below the x-axis. So that's going to correspond with a negative slope. Between -2.5 and 0, all this is sitting above the x-axis. That's going to correspond with a positive slope. Below, it's negative. Above, it's positive. So this is a much better picture as to what your graph will look like. There's going to be a falling until a relative min at -2.5. It's going to rise to a relative max at 0. It's going to fall to some relative min at x equals 2, and then rise after that. Okay, let's create our second derivative sine line. Endpoint still from -3 to 4. But now the critical points that's going to comprise of our points of inflection is found elsewhere, right? It's no longer the x-intercepts. It's going to be the peaks and valleys. If you think about points of inflection on the original graph, those are places where your graph is going to be at its steepest point, right? Either maximum relative positive slope or minimum slope. And so that's how it's going to look on the G prime graph. It's going to be at the highest and lowest point, because this is where relative maximum slope and relative minimum slope is going to occur. These are the steepest points on the graph. Now, to fill in the concavity information, we look at the slope. We define concave up as places where slope is becoming more positive. So wherever slope is becoming more positive, it's going to translate to a concave up shape on the original graph. Negative slope on the derivative graph is going to translate to concave down. Positive slope translates to concave up. Negative slope, concave down. Questions so far? Okay, so now for part C, we're going to build our g of x graph. If we look at the problem here, it says we have some order pairs that's kind of anchoring our graph a little bit. So I want a relative min at negative 2.5. Right now, we don't really care where that point is. But for me, if I'm going to pick a relative min, I'm going to pick a point relatively low on the graph just to make it more obvious. So negative 2.5, I'm going to pick a point just somewhere near the bottom of my coordinate plane. Relative max is at 0. So some point a little bit higher. And then relative minimum at 2. So I'll pick a point a little bit lower. But what I'm really after is the slope patterns. I want the slope patterns to match. So decrease to relative min. I don't care about my concavity just yet. Rises to my relative max, falls to my relative min, and rise again. I want to mark off my potential points of inflections. Wherever my graph lands at -1, I'm going to just give myself a transition point here. At 1, it landed somewhere here for me. 3, it landed somewhere here for me. So I'm just going to be connecting from red dot to red dot with the appropriate curvature. So in the first interval, I want this portion to display concave up. So I'm going back and retracing my graph. Second interval, I'm going to display concave down. From 1 to 3, concave up. And then from 3 to 4, I want concave down. So this problem did not ask for second derivative graph, but you will see it on the test. So let's do that as well. We're going to sketch our second derivative graph. Now, to sketch your second derivative graph, the only thing you need to base this on is off of your sine line, second derivative sine line. It's the only thing you need to look at. Here's my coordinate plane. But the y-axis represents something else, right? It's not location, it's not slope, now it's concavity of the original function. So I like to label what I'm looking at here. X-intercepts are going to be my points of inflection. Between -3 and -1, I want the graph to be, don't worry about the shape, just look at the location. I want my graph to be in this region, right? I'm matching. But it's going to have to go down because it has to connect to this point. So it has to look something like this. And the rest of it, we're just kind of weaving back and forth above and below the x-axis through those target points. From -1 to 1, concave down, it's going to have to reside in this region. So I'm going to make it go down, but it has to come back up at some point. From 1 to 3, above, but it's going to have to come back down. And finally, from 3 to 4, below. Okay, questions? On the test, I'll also be asking you for relative min, relative mass, concave up, all that, but this is secondary, right? So do this at the end with the because statements if you have time, but do everything else first. Right? Okay, I'll have a health session this afternoon, 3:30, either in the classroom or you can join on Teams. It'll be recorded. Morning session, 7:15 tomorrow. Study for your tests. Let me know if you have any questions.
For open notes, are we able to use our quiz?
Yeah, you can use it. Yeah. Have a great day, guys.